Good afternoon, everyone. We are Team Softwel. Today we are here going to present a presentation on topic EWS, that is Early Warning System for Glacial Lake Outburst Floods. Starting with the introduction, Softwel is a private company located in Baneshwar, Kathmandu, and here is our team. Starting with myself, I am Eliza Pradhan. Our next team mate is Pravad Mandal, likely Abhinav Malla, Love Maharjan, and Lasta Manandar. Now, going ahead, starting with the background, Nepal has been gifted with a diverse geographical condition, which make it susceptible to the various disasters. Zooming into the Himalayan region of our country, it has numerous glacial lakes, which are prone to different disasters as well. Due to the changing climate and seismic activities, these glacial lakes can burst at any point of time. Various studies indicate huge loss in lives and property. Due to this reason, a proper end-to-end and people-centered early warning system is required. Now, moving forward with the different studies conducted by ISMOD and UNDP, about 47 potentially dangerous glacial lakes has been identified in the regions like China, Nepal, India, and out of which about 21 PDGLs are identified in Nepal with the highest risk. Now, talking about the existing systems that has been implemented in Nepal currently, different water level sensors has been used for detecting the floods. So when it detects, it's too late to send the messages or early warning systems. Similarly, monitoring being done using the remote sensing, which has significant lag in data retrieval, difficult to judge when to send the warning to the system. Likely, there are radio transmitters used, which are expensive for delivering the messages and which are mostly unmaintained. Lastly, the current system that rely on our ground-based stations, if one of the station fails, other stations may not receive the early warning messages at all. So this makes the system fail at the moment. So for the further explanations, I would like to give the lead to Mr. Abhinav Malla. Thank you. Abhinav.
Thank you, Elza. So our proposed system is to develop a monitoring station that will continuously monitor glacier movements and the movement of the terminal end moraine of glacial lakes at risk using the QZSS Madoka. So it will detect the long-term motion using Madoka, and then we are also including an accelerometer in that monitoring station, which will detect and monitor the rapid motion and issue an warning. So the system will issue an early warning when there is a significant amount of motion. So, and this warning is first issued to an authorized person, and who will then decide whether to issue the warning to everyone. Once an authorized person decides to issue the warning, the early warning is sent to remote settlements using the DC report and the QZSS L1S signal. And the flood levels and safe zones for glacial lake outburst floods can be pre-computed and stored in the early warning stations or in mobile applications. So here is a diagram of our system. So first we have a monitoring station that uses Madoka and Raspberry Pi for monitoring the glacial lake. That will send a periodic broadcast of the position, average position, to a LoRa gateway, which sends it over the internet to our control server. The control server then detects whether to send out the notification and then sends it through the internet to mobile devices in the area, and then also to the QZSS control center, which is then uplinked to the satellite and then transmitted to the Espressen's device as the DC report, which is then used to trigger the sirens and the message boards, LEDs. So here's a short demo of how our system is going to work. This is a video. First, we place Maruka receivers at the terminal ends of the glacial lake. Then as the glacier melts and the lake fills up, it starts to move. So when it's moving, it sends out a broadcast of its position to a control server. Okay. So now it sends a LoRa transmission to our control server, which then sends it to the satellite through our QZSS control center. And from there, we receive the L1S signals and then ring the sirens, and also send out an alert to the mobile app. So once the sirens start ringing, everyone will evacuate to the evacuation area. And then the glacier breaks and there's a glacial lake outburst flood. Okay. So I'm now going to discuss the design and development of our system. So as I said before, we'll use Maruka receiver to monitor the long-term motion and accelerometers to detect sudden movement. So with the Maruka receivers, we do not need internet to obtain a corrected position at the monitoring station, because we cannot rely on internet there. It is in extremely remote areas. So we are sending the average position of that monitoring station every 5 minutes. And we are by also using a satellite-based EWS, we can avoid a single point of failure in the early warning system. So for example, when we have radio relays, so if one of them fails, the downstream stations don't get the early warning. With satellites, all the early warning stations get the warning at the same time. And the expressions device can also be linked to the existing systems. So we can use the same sirens, but triggered by the expressions device from the satellite. So here's our board that we developed for this purpose. So this is an add-on board for Raspberry Pi that we made ourselves. It contains an accelerometer and a LoRa module. And then we are using the Maruka receiver F9P with the uBlocks D9C. So this is then powered by a USB power bank and a solar panel. And so yeah, we have a custom PCB here. And so this is our final setup. So this is the box, which contains the antenna and the solar panel and a LoRa antenna. And inside the box, we have the Raspberry Pi, the battery, and the Maruka receiver. So now here's some details on the packet structure. So we are broadcasting the position publicly without encryption. And to prevent attackers, so for example, someone may just broadcast their own coordinates using their own LoRa receiver. We are signing the data with a digital signature. So the first type of message sent is average position every 5 minutes. It is going to send the time, latitude, longitude, elevation, and the standard deviation of that position. So the second type of message is broadcast when the acceleration is detected. So it is sent out every second without averaging once it detects motion. So these are not average position. These are broadcast every second. So the data is then sent to our EWS server. So it's a web application developed using ASP.NET Core, and it has an API which is called by the LoRa receiver. So the LoRa receiver receives it and calls an API in our system. And this system will detect the movement of glacial lake, and it will also generate EWS messages for the satellite. And it also sends out push notifications to the mobile phones. And you can access this website right now using this link. So in the figure, I have shown the position, station elevation with time, the change in position with time. So it's not much changes here, 10 to 20 centimeters at most. So if there is a outburst flood, it will be changing by a few meters. And that we'll use to output the EWS message. So here's some more screenshots from that website. So we have a database of the glacial lakes at risk, the 21 glacial lakes that we mentioned. And here we can change its status. So when the authorized person needs to issue a warning, they can just change this to flood warning and change status, and it will send out a warning message to everyone. So here's a flow chart of how it is working. So first we receive the position from monitoring stations, then compare it with the initial position of the station. And if the difference is higher than a threshold, we send out an alert to the authority or the authorized person. And if that authorized person decides to issue the warning, we push out the notification to everyone in the affected area by mobile phone, internet, and then we also send the EWS message out for broadcast. So here's what happens when the accelerometer detects motion. So it starts sending position every second to the EWS server using that message type 2, and then also sends alert to that authority. So when they decide to issue the warning, the warning is also issued again to mobile phone and to the QZSS control center. So we're using push notifications using Google Firebase, and automated notification is sent out whenever a possible glacial lake outburst is detected. So we can then also pre-compute the areas of flooding. So for example, here's a glacial lake. So it's a very big one, so Rolpa. And we can predict that, pre-calculate that this area is going to be flooded when this lake bursts based on the digital elevation model and the volume of water in that lake. So, and these polygons can be stored stored in our database and also stored in the mobile applications and early warning stations. And when we broadcast the EWS message, we can just include the ID of these polygons as an extended data. So here's our early warning station. So we're using the Sony Expressens to receive the DC report, and there's an Arduino sketch running on it which parses that DC report and uses its own GPS location to check if it falls in the affected area. And if it does, it will send out a warning siren beep to a speaker and also to LED lights. And we are using a mobile phone connected to the Expressens to provide power to show and to display the debugging information. So here's our early warning station. It's a speaker, Expressens. We are using main and extension board, so LED and a smartphone for display. So here's a demo video. Right now we are using the accelerometer to detect motion, and then it brings up a push notification for saying movement detected. Then we go into the EWS website. So the authorized person will then log in using their username and password, and then go and check the status of that station. So they can check the position logs. Okay, so X coordinate, Y coordinate, elevation. And then they can decide to issue the warning. So they go into details, so change status, flood warning, sent. So it then sends out the EWS message and then also sends the push notification to all the phones. So EWS warning, flood alert. And then the message also comes in from the satellite. So we are logging the output here, and we are hearing the siren, and we also get the push notification around the same time. So here are some technical challenges that we will be facing when we go out to deploy this system. So first of all, we are processing the Madoka data in a Raspberry Pi 3, which is consuming a lot of power. So this thing has to run using battery and solar power. So we want to have a low power receiver. So maybe some of our sponsors may be able to build a monitoring the Madoka receiver, low power Madoka receiver in a microcontroller form. And first, the second challenge is to get the early warning message from the glacial lake to the satellite. So we're using LoRa right now, and to transmit it up to a region where there is internet access. Instead of this, we can also be using satellite uplink or downlink. And then the third challenge is to deploy the monitoring station. So how do we take it to that remote glacial lake and then set it up there? So one option is to make it as light as possible and then carry it using drones, UAVs. So some future advancements that we are planning. So right now we are only outputting position. So we can also use velocity data and collect, as we collect more data, we will be able to make more accurate models to predict glacial lake outburst events ahead of time, which will allow more time for people to evacuate. And the next task would be to determine safe zones for all risky glacial lakes in Nepal and develop apps that will guide people to their nearest safe zones using their own location. So, and the third task would be to automate the observation of glacial lakes using drones when we detect a movement. So right now, the authorized person has to decide based on the position output of that Maroka receiver. So we are planning to try out drones, which will be sent automatically for data capture. And based on the data collected, the images, the concerned authority can decide whether or not to issue the warning. So thank you. That's our presentation. We would like to thank all our the MGA and all the sponsors for this organizing this RPD challenge.